Hello, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be going over caching strategies for my Next.js e-commerce platform, ISR, HTTP headers, and what I'd cache with Redis when it calls for it. Caching is one of those topics that feels like an optimization, something you'll get to later after launch when traffic picks up. But caching is not just about speed. It's about controlling the cost of every request that reaches your database and your server. Here's the math that makes this concrete. At 100,000 requests per second with a 90% cache hit rate, 1,000 requests per second reach your database. Improve that to 95% and only 500 do. Improve that from 95 to 99% and you go from 500 database queries per second down to 100. A 5x reduction for 4 percentage points. The relationship is nonlinear. The last few percentage points of hit rate have disproportionate impact on your infrastructure costs, and that makes hit rate the most important number in your caching strategy. I'm building an e-commerce platform with Next.js, and caching shows up at 3 layers. ISR for page level caching, cache control headers for browser and CDN control, and in-memory rate limiter designed to swap to upstash Redis when I need distributed caching. This video is about how I think about each layer, what I use today, and what I'd add with Redis. So the cache hierarchy. Every request passes through multiple caches before it hits the database. Understanding the hierarchy means understanding both the latency and the consistency trade-offs at each layer. So we have browser cache, approximately 0 milliseconds, static assets, JavaScript bundles, CSS, images are cached locally with content address URLs. When the file changes, the URL changes, so the browser fetches the new version automatically. Vercel CDN edge, 5 to 50 milliseconds depending on the user's geographic distance from the nearest edge node. When a page is ISR cached, it is served entirely from the edge without touching my server or my database. Redis, when I add it, 1 to 5 milliseconds round trip, fast enough that most applications don't notice the overhead, but every cache miss adds real latency. Postgres shared buffers. Sub-millisecond for hot data. The database caches frequently across data pages in RAM. A product page viewed 100 times in a minute only reads from the disk once. Whole database reads from disk, 10 to 100 milliseconds, plus query planning and execution time. This is the floor you're trying to avoid on every request. Hit rate, the nonlinear math that is significant. At 10,000 requests per second, the table tells the story clearly. At 60% hit rate, 4,000 database queries per second, overwhelmed at most scales. At 80%, 2,000. At 90%, 1,000. Good CDN configuration gets you there. At 95%, 500. That's proper ISR plus cache control headers. At 99%, that's 100. An 80% reduction from the 95% baseline. At 99.9%, that's 10. Here's the critical insight. Going from 90% to 95% reduces the database load by 50%. Going from 95% to 99% also reduces database load by 80%, but over a much smaller change in the hit rate. The relationship is nonlinear. The last few percentage points are worth disproportionately more than the first 90%. That is why hit rate is the most headline metric. It's what drives everything from infrastructure sizing to monthly spend. ISR, Stale-While-Revalidate. The caching mechanism I use most in Next.js, incremental static regeneration. When a user requests a blog post, Next.js checks the edge cache. If the page is cached and within the revalidation window, it is served immediately from the edge, typically 5 to 50 milliseconds. If the page has expired, my blog posts revalidate every 300 seconds. Next.js serves the stale cache version immediately and triggers a background regeneration. The next user sees the fresh version. No user ever waits for a regeneration to complete. For on-demand revalidation, when I update a blog post, my server action calls revalidate path to regenerate that specific page immediately. The most important implication for e-commerce is the price correctness rule on the right side of the slide. The display price of an ISR cache product page can be up to 5 minutes stale. That is acceptable and intentional. A price update takes a few minutes to appear. What is not acceptable is using the cache display price as the checkout price. The checkout server action must always read the current price from the database, never the cache, never from the page display value. The price manipulation attack. The item on sale. User adds to cart. The sale ends. Cache displays shows the old price. An attacker checks out at the sale price. The fix is structural. Checkout always reads from the database. Display price and checkout price are explicitly different fields. Cache control headers. For content served outside of ISR, API responses, static assets, authenticated pages, I use HTTP cache control headers. 2 directives specifically. Max age controls the browser cache, and smax age controls shared caches. CDNs. By setting both, you give CDN nodes a longer cache lifetime than browsers. Cache control. Public. Max age 300. Smax age 3600. This means the browser checks for updates every 5 minutes, but the CDN serves the same copy for an hour. There's also Stale-While-Revalidate as a cache control directive. Stale-While-Revalidate is assigned to 60. This tells the browser and the CDN to serve stale content for up to 60 seconds past the max age, while fetching a fresh copy in the background. It eliminates the latency hit of cache misses for users whose request slightly expired content. My strategy by data type. Public product data gets public. Max age of 300, max age of 3600. Stale-While-Revalidate of 60. Authenticated user data gets private no store. The CDN must never cache user-specific content. Order status and payment confirmations get no store. Static assets get public. Max age, you see the number on the screen, right? And it's immutable. 1 year, never revalidated. One thing that's worth noting, ISR and cache control stack. The ISR TTL controls how long the edge serves the statically generated HTML before regenerating. The cache control header controls how long the browser caches it before requesting that from the edge again. The worst case staleness from a user's perspective is the sum of both. What I'd cache with Redis. I currently don't have Redis instance today. My traffic does not justify it, but I've designed my rate limiter with an abstracted store interface, which is very easy to swap in Upstash Redis with a single environment variable. There are 4 cache patterns mapped to my use cases. Cache aside for product data. Read heavy data where misses are acceptable. The application checks Redis first. On a miss, it queries Supabase and populates Redis with a TTL. A product page cache miss just means one database read, right through, for user profiles. When cache misses feel broken to users, when a profile is updated, the application writes to both the database and Redis simultaneously. Cache is always warm. Redis Atomic, INCR for rate limit counters. INCR is a single atomic server-side operation. Moving from in-memory map to Redis provides distributed enforcement across all serverless function instances. In-memory counters reset on cold start. Redis counters persist. Write around for order confirmations written once and recipient reads it once. Skip the cache on write. Populate lazily on the first read. Cache invalidation. This is the hard part. The mechanics of cache invalidation are simple. Delete a key from Redis. The difficulty is ensuring invalidation happens in every code path that modifies the underlying data, and that it happens correctly relative to the write. Here's the race condition a single delete leaves open. Thread A experiences a cache miss and reads the old value from the database. Thread B writes the new data to the database and deletes the cache key. Thread A, having just read the old value, populates the cache with stale value. Thread B's invalidation achieved nothing. The double delete pattern closes both windows. Delete the cache key before the database write. This catches thread A if it hasn't cached yet. Perform the write. Delete the cache key again after a short delay. This catches thread A if it's cached between the write and the first delete. 2 deletes, 2 windows closed. For ISR pages, invalidation is the co-located with mutation. When I update a blog post, the server action calls revalidate path immediate after the database write. Same function, same call. The underlying principle, invalidation must be part of the write path, not an afterthought. Every server action that changes cache data includes an invalidation step in the same function. Cache stampede prevention. A hotkey expires. The featured product on your homepage, for instance. At that moment, 200 concurrent requests all experience a cache miss simultaneously. All 200 query the database for the same data. The database, sized for 10 queries per second in steady state, suddenly receives 200. It saturates, response time spike, users see errors. This is not theoretical. It happens whenever a popular cache key expires under meaningful traffic. We have 3 solutions here. The mutex cache pattern. On cache miss, before querying the database, attempt to acquire a short TTL Redis lock. If you get the lock, query the database, populate the cache, release the lock. If you don't, wait briefly and retry the cache read. By the time the lock releases, the cache is warm. All requests except the lock holder served from cache. Probabilistic early expiry. As the TTL approaches 0, a random function of request proactively refresh the cache before expiry. More elegant but more complex to implement correctly. And we have, for ISR pages, Next.js handles Stampede prevention natively. Only one regeneration runs at a time. All other requests see the cached version. What I never cache. Some data must always be read from the authoritative source. Account balances. A stale balance enables overspend or denial of valid spend. What I never cache. Some data must be read from the authoritative source. Account balances. A stale balance enables overspend or denial of valid spend. Live inventory counts. A stale count causes oversell. Payment and transaction state. Item potency and status must be authoritative. Access control decisions for the current request. A stale deny locks out a valid user. A stale allow is a security vulnerability. One-time tokens. Password reset links. Email verification codes. Caching enables replay attacks. Audit log writes. Must be durable immediately, and that's part of the same transaction as the primary operation. Prices during checkout deserve a specific mention because it becomes a security consideration, not just a correctness one. The price manipulation attack. A user adds an item to their cart while it's on sale. The displayed price gets cached. The sale ends. If your checkout reads the cached display price instead of the current database price, the attacker checks out at the sale price after the sale ended. The checkout server action must always reread prices from the database, regardless of what the product page showed. Simple rule: if stale data causes financial loss, a security vulnerability, or a regulatory violation, read from the source of truth. Cache observability, the metrics that matter. Caching without observability is guesswork. 4 metrics that actually matter. The hit rate. This is the headline metric. At 10,000 requests a second, the difference between 95% and a 99% hit rate is 500 versus 100 database queries per second. That alerts when hit rate drops more than 5% below baseline. The miss rate. This tracks separately to understand why misses happen. Cold start misses are expected. Expired key misses are expected. Keys that should be present but aren't indicate an invalidation bug. Eviction rate. Keys evicted before their TTL expires because the cache ran out of memory. Any sustained eviction rate means your cache is undersized. Items being pushed out before they expire mean your effective hit rate is lower than your TTL-based math would suggest. Redis P99 latency. A P99 of 50 milliseconds means 1% of requests touching the cache adds 50 milliseconds of overhead. You should know the number. A note on alert thresholds. Ensure your baseline rejection rate for a week after launch, then set thresholds relative to that baseline. Say, alert when the metric is 3 times the baseline. Absolute thresholds without baseline produce either alert fatigue or missed problems. Caching is a consistency contract. When you cache something, you are making an explicit promise. Data up to TTL seconds old is acceptable for this use case. Every caching decision should begin with that question. Am I comfortable with a user seeing data that is X seconds old? The hit rate is the headline metric. The relationship is nonlinear. The last 4 percentage points, 95 to 99%, reduces database load by 80%. That's where the infrastructure savings are. ISR Stale-While-Revalidate. Displayed price can be up to 5 minutes stale. That is acceptable. Checkout price must always read fresh from the database. That is a correctness requirement, not a performance choice. The cache control layers. Max age controls browser. S max age control CDN. Stale-While-Revalidate eliminates the latency hit of cache misses. Authenticated response. Private, no store. The CDN must never cache user data. Invalidation in the right path, not as an afterthought. Doubly delete patterns, close the race window. 2 deletes, 2 windows closed. Things to never cache. I choose not to cache. Account balances, inventory count, payment state, access control decisions, one-time tokens, audit log writes. If stale data causes financial loss or a security vulnerability, read from source. And for a client, caching on this platform uses ISR at the page layer. Cache control headers for API responses and explicit rules about what is never cached. Checkout prices always read from the database. Authenticated users never stored by the CDN. Cache invalidation is co-located with every mutation that changes cache data. I'm Fleshed Out Thoughts, and I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're designing cache for your own platform, ISR configuration, cache control strategy, or Redis architecture, reach out. I'm open to freelance projects and consulting. The full post is linked in the description. Complete cache control header configuration, the Redis cache aside and write through implementation, and a decision table for choosing between caching patterns. Next in the series, CAP theorem and consistency models, how I choose between strong and eventual consistency for orders, products, and search. I'll see you there.